Okay, so for today, the first thing that we need to talk about is the homework from last night. Again, I have all the answers up here. I also handwritten in the values in terms of pi for the first worksheet. Again, either way is fine. I didn't do that on the second one, but these are the answers. If you want me to go back and work one out, just let me know. But these are the answers. One, we had 615.8 inches squared. Two, 3,217 meters squared. Three was 603.2 yards squared. Four, 114.4 inches squared. On five, you had 2,226.1 centimeters cubed. On six, 446,091.2 feet cubed. On seven, 28,952.9 yards cubed. And finally, number eight, 296.8 meters cubed. Any questions on any of those? Yes. One? You said one, right? One and four. All right. On number one, so again, surface area, you have to know your formula for surface area, which on this one, our surface area formula for a sphere is surface area equals 4 pi r squared. All we need is the radius. So we have the radius is 7. We're just plugging it in. So we have surface area equals 4 times pi 7 squared. 7 squared is 49. 4 times 49 gives us 196. And then multiply out by pi, which gave us the 615.8. Again, these were in inches squared. Then on number 3, it's talking about a hemisphere. The only difference between a sphere and a hemisphere is that the surface area formula now calls for 3 pi r squared. So for surface area on this one, surface area equals 3 pi. The radius they gave us was 8 squared. 8 squared, that's going to be 64. 64 times 3, that's going to give us 192. And then that's in terms of pi, multiply it out, and that's where you get your answer of 603.2. Again, those were in yards squared. Any other questions that you want me to go over? Yes. 5? All right, so on 5, this one's doing volume. Yeah, let me scoot this up. So on 5, we're looking at volume of a sphere, which is going to be 4/3 pi r cubed. Now, this one had a decimal for my diameter to start off. But again, that's my diameter. I need my radius, so I have to do half of that. The radius here is going to be 8.1. So once I know what the radius is, I'm just plugging it in. Volume equals 4/3 pi r cubed. So 8.1 has to be cubed. All right, so 531.441 multiply by 4, divide by 3. So times 4, divide by 3. You get 708.588 pi. and then you gotta multiply by 3.14, and that gives you that final value of 2226.1. Which one? 7? Sure. So this one was a hemisphere. Again, difference between hemisphere and sphere. Now we're doing 2/3 instead of 4/3. Again, everything else is the same. And then we're just plugging in. They told us that we had 48 for the diameter. So the radius would have been half of that, which is 24. So when we plug in, we have volume equals 2/3 pi 24 cubed. First, 24 cubed is a really big number. 2/3 13,824. Multiply it by 2, divide it by 3. We get 9,216 pi. And then multiply by pi, and you get your answer of 28,952.9. Let's go ahead and go on to the other side. All right, on this side, again, reading them off, I did not put terms of pi on these. Again, if you need me to go to any of them, I can do that in just a minute. So number 1, correct answer there, 530.9 centimeters squared. Number 2, 24,884.6 feet squared. Number 3, that was 665 inches squared. 4 was 119.2 meters squared. Number 5, we had 7,832.9 feet cubed. Number 6, 8,578.6 meters cubed. Number 8, 1,526.8 millimeters cubed. And finally, number 8, 787.9 yards cubed. All right. Any on that page that you let me go back to? Yes. 6, sure. All right, so 6 gave you a diagram of a hemisphere. They also gave you the diameter. We need the radius. So if the diameter is 32, the diameter is 32, the radius here is 16. Again, formula for this was asking for volume. So we have volume equals 2/3 pi r cubed. So that's 16 cubed. 16 cubed is, oops, I should write it in. That's 4,096. Then we take that 4,096 and multiply it by 2, divide it by 3, and we get 2,700. Yeah, okay. For a second, I thought that in wrong. 2,730.6 pi, and then multiply out pi, and you get your final answer of 8,578.64, rounded off to just 6, and that's our answer. Again, units cubed, so meters cubed. Anything else from last time? All right, on that one, so they gave us a circumference, so there's a little extra work there. Let me move this up. Okay, so on, you said number 8, right? Oh, and I forgot to show this answer. For number 9, it was 7,986.4 inches cubed. All right. Now, for number 8, they gave us circumference. So we did have to actually use our circumference formula first to find our radius. Our circumference formula is 2 pi r. So they gave us a circumference of 36. 36 equals 2 pi r. First, divide off 2. That gives us 18 equals pi times r. Divide off pi, and we get our radius. Which which is 5.7296. Let's round it. I leave that on your calculator until you're ready to do something else here, because now we got to plug that in. I'm going to plug that in. We're looking for a sphere on this one. Do number 8. So volume of a sphere, 4/3 pi radius cubed. So we're plugging that in for our radius. We have 5.729 raised to the 3rd power, and then multiplied by 4, divided by 3, gives us 250. Again, keep a couple extra decimals, multiply that by pi, and you have your answer, which is 7.87. All right. Okay, let's move on to today's stuff. So clear that. All right, today. Oops. That's around the corner. Let's see it though. It might be covered. All right. Like I said, first we're going to go, and I'm going to write on a plain sheet here. We have to talk about our similar figures. Now, we've talked about similar figures before. Whenever we have similar figures, what are we dealing with? Figures that are the same blank but different blank. Same shape, all right, so same shape, but different size. If they were same shape, same size, then they'd be congruent. Again, similar shape, different size. That's a similar figure. So similar figures, same shape, different size. Now, we did this a lot when we talked about triangles. That was the main thing that we covered, but we did do some other polygons as well. We talked about some figures that were always going to be the same or similar figures, and that was any shape that was the regular figures. So like things like equilateral triangles were always similar. Squares, because they're regular polygons as well, are going to be similar figures all the time. Now, not every rectangle is always going to be similar, but I'm going to draw 2 on here. So I'm going to draw a 3, 4, 5 triangle. And I'm going to draw another triangle that's similar to it. It's probably not going to be drawn to scale, but it's our 6, 8, 10. And these 2 are similar. All right. Now, how do we know for sure that they are similar? All the sides are multiplied by 2. So if we were to compare the sides here, the scale factor, which is the ratio that compares the sides, is 1 to 2. Because if you took any of those sides and matched them up, you have that same ratio. 3 to 6 reduces to 1/2. 5 to 10 reduces to 1/2. 4 to 8 reduces to 1/2. When you have similar figures, angles are going to be congruent, sides are going to be proportional. All right. So that's kind of a recap. Now, what we need to look at is we need to look at some of the other things that are going to have patterns when dealing with similar figures. So we've already talked about scale factor. The next thing we need to talk about is area. So we know that our scale factor in this one is 1 to 2. Now I know, what about the area ratio. So what's the ratio of the two areas of these two shapes? Well, in order to compare that, we're going to need to look at something else. We have to find the area. So how do I find the area of these? Now that we've done area of a triangle is found by doing what formula? Just base down side? One half. Okay, I might have missed that. All right. 1/2 base times height. Now, in a triangle, how do you identify what's going to be used as your base and height when doing area? So look at that triangle. What two parts are we going to use for base and height in this figure, and why? Am I going to use a 5 because it's on bottom? No. Who am I going to use? 4. Okay, and the 3. Why those two? Okay, they are the legs of that right triangle. You're kind of on the right direction there. They are perpendicular. Those are the two sides that are perpendicular from each other. Again, base and height always have to be perpendicular lengths. So on here we can use 3 and 4 as our base and height. So let's solve this. We have area equals 1/2 base and height. Doesn't matter which one you use where, but 1/2 of 4 is 2. 2 times 3 is 6. So my area on this one is 6. Down here, same thing. Area 1/2 base times height. Yeah, I'm going to use the same two pieces. So 8 and 6. 1/2 of 8 is 4. 4 times 6 is 24. So if I wanted to write a ratio of the two areas, this area is 6. This one's 24. I wrote this really good. I'm going to save room because I'm going to run out of space for what I want to write. I'm going to rewrite this just a little bit smaller. Again, you guys are writing on your own paper, so shouldn't matter to you guys. I'm rewriting the exact same thing. One half. All right. So area ratio, we have 6 over 24. Can we reduce that? Yeah. How many times does 6 go into 24? 4 times. So if I reduce both of those numbers by 6, I get 1 over 4. All right. Now, there's a relationship here between our scale factor and that area ratio. Before we talk about what that is, let's look at another shape. All right. If we look at a square, we're now looking at a square. Here I have a square. I'm going to say my sides are all 3 in this square. And then I'm going to have another square. Oh, that's a horrible square. Let me draw that. Again, it might not be to scale. I'm going to say my sides are 9 on this one. So I want to look at the same two things. What is my scale factor? What is my area ratio? So first, my scale factor. What's my scale factor between these two images? Third, 1 to 3. Anybody want to take a guess what the area ratio might be? What's your guess? 1 over 9. All right, let's see if it works out. So if we do the area formula for a square is base times height. So on this one, it's just 3 times 3. On this one down here, it's 9 times 9. So what's my area for the top one? 3 times 3 is? And 9 times 9 is? So I have two numbers to compare. I have 9 and 81. Does that equal 1/9? Whoa. Does that, hold on. Does that equal 1/9? Yes, it does. Sorry. So on here, look at these two values and look at these two values. How does our scale factor compare to our area ratio or vice versa? All right, maybe they. Times by itself. Another way to say that is it is raised to the second power or squared. All right. But yes, you have the right idea. So it's multiplied by itself. So on here, our area ratio is essentially going to be our scale factor squared. All right. Now this pattern continues. So these are two-dimensional figures. Now we're looking at three-dimensional figures. So instead of just talking about some figures, I'm going to talk about similar solids. So now we're talking about 3D figures. And let's look at the first shape is going to be our cube. So on this cube, now since we just did the square, that was 3s. I'm going to use 3s for our sides here as well. And then the other one, since I use 9 for my other one, I'm going to do the same thing here. No. All right, so I have two cubes. Just like with our two-dimensional figures, if we have a regular three-dimensional figure, they're also always going to be similar. So I don't have to worry about looking at the sides and matching it up and checking my scale factors right now. But all the sides are proportional, just like they were with our 2D images, right? So on here, I want to look at a couple of things. I want to look at our scale factor. I want to look at our area ratio. I want to look at my surface area ratio. And I want to look at the volume ratio. So on here, we have the scale factor. The scale factor, we already looked at these values on the previous slide, right? What was our scale factor here? 1/3, right? We had 3 to 9, which reduced to 1/3. Our area ratio we just did on the last slide was what? It was what? 0.9. And what we said about that was this was our scale factor squared. So now we have two other ratios to look at. Surface area and volume. How are they going to relate to our original scale factor? So on here, anybody want to take a guess for our surface area and our volume ratios? Yeah, it's just a guess. You don't have to be right. Anybody want to take a guess for surface area and volume ratios? So, okay, so we're gonna do that part, but do you have a guess first?
Oh,
Do you have a guess? So we're gonna look at the area, we're gonna find the surface area, but do you have a guess? How do you think they're related?
um,
Do you think they might be?
school.
What's gonna be squared?
Like you said, like the last one, that times itself.
Okay, so this is gonna be what? What's your guess?
That would be
You think it's gonna be 109, all right, what's your guess here?
going to be, well,
Grade one. All right, let's see. All right, let's check them. All right. Again, I'm not telling you if they're right yet or not. So looking at these two figures, we have to find surface area and we have to find volume. Now, there are many ways you can find surface area on these. We already know one of the sides, right? We know our area of the base for this one was 9, and we figured out the area of the base of this one was 81. We already did that on the other side, right? There's a fast way that we can do surface area for a cube. All our sides are exactly the same. So that base area is the same area that's on every single one of those bases. How many bases does the cube have? 6 sides, just like it does, right? So we just do 9 times 6. Our surface area here is 9 times 6 is 54. All right, same thing here. So surface area, we have a cube. Fast way to do this, since all the sides are the same, just multiply by 6. And 81 times 6 is. We know 81 times 6? 486. All right, so we have our surface areas. So let's see if you're right about this first one. We have 54 over 486. Does that reduce nicely? How many times does 54 go into 486? 486 divided by 54 is 1/9. So our surface ratio, so our surface area ratio is also our scale factor squared. So now, the volume ratio. You still good with the 1 over 81?
Yeah.
All right. So now, volume. Volume on here is base area times height. Well, we have base area was 9. What's the height? 3. So 9 times 3 is? All right. On the next one, we had our, again, we know our base area. Our base area was 81. Our height on this one is 9. So 81 times 9 is 729. How did I draw the cube? Let me finish this idea and I'll show you how to draw the cube. All right. So we have 729 was our volume. So now compare them. Let's see. 27, 729. I don't know, that's looking like it's not going to be 81. What's it going to be? 27. So how does that relate back to my surface area? So you had the right idea. Instead of it, you square this one, right? But you relate it all the way back to our surface area. It's our surface area cubed. So you multiply by 3 one too many times. But you had the right idea. So scale factor cube. So just to simplify this a little bit. And again, if you don't know the terms, I'm gonna write it out this time, scale factor, which I always use SF. You can also use K for scale factor. Again, that's something we used in that first chapter. Alright, so scale factor, area ratio. And our volume ratio. So if I had x over y, this would be x squared over y squared. This would be x cubed over y cubed. All right. An easy way to think about this is our scale factor, we said, applies to any single dimensional measurement. So length, width, height, any other random lines that you drew into your shape, scale factor applies to. Even perimeter, because it's a single dimensional measurement. When you get over to surface area or even area of the base or any of the areas, area is always a two-dimensional measurement, which our units are always squared. So you take scale factor and you square it, that gives our ratio for area. Volume is a three-dimensional measurement, right? All of our units are in cubed units. So if we take that scale factor and cube it, that'll give us the ratio for our volumes. Now, you can use these to find these missing pieces. So just like we did in the very first section we did on similarity, if we wanted to solve for one of the missing side lengths, we took our scale factor, we set it equal to another fraction and found the missing length. We can do the same thing now with area and volume without going through and finding all the individual pieces. All right. Now, there are other things to this chapter, so I'm going to use a couple examples from that page that I had handed out. But are there any questions here? And I'll show you the two. So let's see. All right. If you want to draw a cube, you can draw first a square. And I don't always start off this way. But if you draw a square and you want to draw a cube, then you're going to draw three lines that are going the same length back at an angle. All right. And then we should connect them. And when we connect them, these lines have to be parallel with each other. And those lines have to be parallel with each other. And then there's a point right here that I use. That's going to be in line with these back 2 points. And it should be that same line that I drew back. And I can draw it as that. A line straight down. That's that. And a line straight over. Yeah. Yep. All right. Any other questions? No? All right, let's go to some examples then. With that. Switch this to this one. Let's see. All right. So now this page. Now there's some overlap with things that we did earlier in the year. So the first thing on the bottom of this page is actually not like the examples I just did, but it's based off of some of the things I said at the beginning. So when we talk about our three-dimensional shapes, they use a lot of the same properties as what we had with our similar figures at the beginning. Our sides, all of our single-dimensional measurements have to be proportional in each image. So on here, the first thing they ask us to do is to identify whether these figures are similar, congruent, or neither. Well, in order for them to be similar, they have to be the same shape, but different sizes. And those side lengths have to be proportional. So looking at the side lengths here, first they have 1 centimeter and 5 centimeters. If I was to do a ratio, my bad. Crazy number. Oh, not that. If I was to match up these two sides, or actually those two heights, you have a ratio of 5 to 1. If we were to look at the two parts on the bottom, 2 and 10, well, 2 over 10 also reduces down to 5 to 1, or 1 to 5. And how you look at it. Are they the same? Yeah. So since we have the exact same ratio for both that height and our side length, these two images must be proportional, which makes them similar. So these two are similar. What is our scale factor? It's that 1 to 5 ratio that we just found. Scale factor is on number 2. Are these two similar, congruent, or neither? What was it? Congruent. All the measurements are the same. So this one is going to be congruent. All right. What about number 3? These two are similar. Why? So you are right, they are similar. Why are they similar? Same, okay, they're same shape, different size. All right, that's true. Can we ever have two spheres that are not similar? No. So just like in our two-dimensional shapes, there was several shapes that were always similar. Our regular polygons are always similar, and our circles are always similar. For our three-dimensional shapes, our regular polyhedrons are always similar, and our spheres are always similar. If you were to look at this with all the dimensions, think about if I was to draw a radius straight back. Well, it's the same radius, right? So they share the same ratio between those pieces. Same thing if I went vertically and went straight down. Here I'd have 4, here I'd have 8. All these single dimensional measurements are always going to be the same in a sphere, no matter what. So they will always be similar. And on this one, our scale factor would be 4 to 8 or 1/2. What about number 4? Are they similar, congruent, or neither? Why do you say neither? What do you mean by none of them are the same? They weren't the same here. Okay. Yeah, so they reduce the same values. Here, if I was to match them up, so I have 2 to 1 for the one piece, right? That's 2 to 1. But if I did the other pieces, 4 to 3, are those equal? No, they're not proportional. So they're not similar. These are going to be neither. All right. Moving on to the other page. Okay, on here. So now we can apply some of these ratios. So number 1, 2 cubes have the same length of 3 and 8. What's the ratio of the surface area of the small cube to the surface area of the large cube? Well, if the scale factor is 3 to 8, the ratio of the volumes, or sorry, ratio of the surface area they asked for is going to be what? What do we have to do to this? Squared. So we got to do 3 squared and 8 squared, which is 9 over 64. Item 2, these similar cones have a height of 3 and 12. What is the ratio of the volume of the small cone to the large cone? So again, scale factor here is 3 to 12. So now ratio of the volume would be Q. All right, your assignment is the back. Now listen, if you aren't here tomorrow I'm passing out a review. This is our last new thing. So if you aren't here tomorrow, just stop by my room sometime. So some of you might have testing in the morning, pick up the review, or you can get it from Candace. That's me covered. I should review that first question anyway. Have a good day.
So I wasn't here on Fridays.